Okay, I want to talk a little bit about inverse functions today, at least get a start on them. So, we got our function machine all set up and ready to go. And here's kind of the issue we got today. So, we got our function machine and we got this rule, right? So, remember how the function machine works. We have maybe we can picture a conveyor belt up here, and we got some numbers and they're cruising along the conveyor belt and they fall into the machine. The machine performs the rule, and they spit out the answer. So this here are the answers that we got. This is the end result. Here, I guess they just fell off into the floor here. Um, so the question I have is, okay, these are our end results. What numbers were originally on the first conveyor belt here? What numbers uh, which ones fell into the machine? What did we start with? So why don't you pause the video right now and see if you can just reverse engineer this maybe and figure out which numbers originally were up here that started this whole process. Okay, so hopefully you paused the video, maybe thought about it for a little bit. If not, let me show you how maybe I would do it. Well, okay, so maybe with this function it's easy enough not that you don't have to run this process. But for a sufficiently complex function, let me show you how I would do this. So if our rule, in fact, let me get black back out here. Our rule was y equals 1/2 of x plus 1. So if I wanted to work backwards and figure out um, what originally was on that top conveyor belt, I'm just going to basically solve for x, right? Because I want to know what was my original x value. So I'm going to subtract 1. I'm going to get 1/2 x equals y minus 1. And then I'm going to multiply by 2. Okay, and then my answer is going to be x equals 2 times y minus 1. And that's going to give me what I originally started with, right? Because I started with x values and it's spitting out y values. That's how my function was originally um, set up to run. So let's kind of run through this process. So if I put in 4 to this function, 4 minus 1 is 3, and 3 times 2 is 6. So 6 must have been originally on my conveyor belt. And let's run it through the process. So let's kind of make sure this works. Half of 6 would be 3. 3 plus 1, sure enough, is 4. So it worked for that one. We plug in 1 for y here. So remember, we're plugging 1 in here for y. Yeah, 1 minus 1 is 0, so the whole thing is 0. So we have 0 was originally on my conveyor belt. And then negative 5. So negative 5 minus 1 is negative 6 times 2 is negative 12. So that was also original on my conveyor belt. So those are my original 3. So this process here is an example of finding an inverse function. Okay, so an inverse essentially is, here are my answers. What did I start with? That's kind of the idea that we need to think of when we think of inverses. And the only kind of bad thing about this is you kind of see this is a little funky. We're not used to really seeing x equals stuff. Not that there's anything wrong with that. It's just not something that we naturally see. So let me show you kind of probably the more conventional way to do this. So if your book or you just for some reason need to suddenly figure out an inverse, here's typically what you see. Typically people tell you you're going to switch your x and y first thing. So x goes there, y goes there. And then you're going to solve for y. So you switch x and y and then solve for y. Okay, so now if I solve for y, this is not going to be a surprise because it's going to be essentially the same thing we have on the left there. Only now that we've taken the time to switch our variables around, now it looks a little bit more, I guess, normal to us, right? We're used to seeing y equals some expression over here. So the way on the right is probably going to be the better way to write these inverses, so we have a y equals sort of function, because down the line we're going to end up graphing these, and certainly we'd rather graph something that's set equal to y rather than something that's set equal to x. So one important thing to notice is that our x and our y switch spots, so to speak. So the x values of our original, so here's our original expression here, well, I guess, and also here. So the x values there are going to become the y values of this equation down here, because, essentially our x and our y have switched spots. So our x values of 1 is going to be the y value of its inverse. And that's going to be an important fact that we use over and over in this section. Let's scroll down just a little bit and do an example that's going to look a lot like your homework problems. So let's say if f of x equals 3x minus 1, find, I'm going to throw some notation at you here, f inverse of x. So you see this notation. It looks like an exponent to the -1. That's read f inverse of x. And literally, it just means to do the process that we were doing up there. Okay? So hopefully you guys remember from Algebra 1, if we have f of x equals something, we can always write that as y equals 3x minus 1. F of x is just another way to write y equals in a way. So once we do that, now we're going to switch our variables. So notice the x takes place of the y takes place of the x. And then we're just going to solve for y. So now I need to solve for y. So 3y equals x plus 1. And if I divide by 3, y is going to equal x plus 1 over 3. So there we go. And again, you should notice that, this whole process is kicked off by switching the places of x and y. So again, x values from one become y values from the other one. And so let me just kind of really, really drive home that sort of point, that sort of switching, that idea that the x and y values switch. So let's look at inverses. Let's just have a table of values. So let's say I was going to look at a function that was not defined by a rule. It was just defined as just a kind of an assortment of ordered pairs here. We'll try to make the best chart I can. Okay, so we'll call that f of x because I'm not very creative. All right, let's say, I don't know, let's not use any crazy numbers here. So I don't know what the rule for f of x is, but let's say if I put in 1, I get 5. If I put in 2, I get 11. If I put in 3, I get -7. If I put in pi, I get 2 pi. If I put in 1.9, I get 7. And if I put in 12, I get 0. I don't know what kind of crazy rule that is that's assigning these values, but let's just say for the sake of argument, that's what happened. So let's think, what would the chart of f inverse look like? So I want to look at f inverse now. And if you kind of recall the process, it says you should switch x and y. That's how you kick off that inverse finding process. And with a chart, I mean, it's even easier than what probably using a rule, a function rule is, because literally you just switch the x and the y values. So if I have, so my y values, those are my function values, my f of x values. So all of these original function values become the x values for my inverse chart. So 5, I got 11, I've got -7, I've got 2 pi, 7, and 0. And then all of the x values in my original function in f become y values or function values down here in f inverse. So hopefully you can see what's going on here. I'm just taking my x's and y's and switching spots. Just like I did with a function, right? You can up here still, I just took my x and y and they just switched locations. Same deal with the chart here. These y values become x values and x values become y values. Whoops, let me clear my screen here. So we do have an important point here. So I think I want to start this by listing the domain and range of f and listing the domain and range of f inverse. So here real quick, the domain, so we'll just say D for domain, of f would just be 1, 2, 3, pi, all the x values, right? The domain is all the x values. So kind of sloppy, but there we go. And then the range would just be the list of the y values. Now let's see what happens when we kind of switch over to f inverse here. So the domain for f inverse, 5, 11, -7, 2 pi, 7, 0. In no particular, notice I didn't really bother to arrange that in a particular order, just the order I saw it. So if that annoys anyone, I'm sorry. And then the range is all the y values. But let's look in relation to each other. The range from the original becomes the domain of the inverse and vice versa. So the domain of one becomes the range of the other. And, you know, it goes both ways there. So that's a nice important point. It's a good little generalization. That's not specific to this pair of functions. You know, any function in its inverse is going to have this sort of domain and range switching action. And that's important to note. Okay, so anytime we have that function in its inverse and we want to think about its domain and its range, they're going to switch places. The domain of one is the range of the other and vice versa. So we have one more example to do, and we only have 3 minutes to do it. So I'm going to try to be as speedy as I can about it. And we're going to keep that domain idea in our minds when we do this example. And it's not going to be a super apparent why until the very end. So let's let f of x equal the square root of x minus 2. And let's say we want to find, obviously, f inverse. So again, here's the strategy. First things first, we need to write f of x as y and rewrite our function. Then we need to switch the x and y and solve for y. So in this particular case, the first thing I'm going to do is square both sides to cancel my square root here. So I get x squared equals y minus 2. And then I need to add 2. And so y is going to equal x squared plus 2. And so now that I've solved for y, that is my inverse. So f inverse is going to equal x squared plus 2. So now we need to, I like to think about, well, what's the domain of this function? And we just said that the domain of this function is going to be the range of our original function. So now we need to think, well, what is the range of that crazy square root function? And maybe it's easier to look at it from a graphical perspective. Remember, that is just the parent square root function that's been moved 2 to the right. So let's go 1, 2, and I'm going to do a real quick sketch here. But it's going to look something like this. And we remember the range is the y values. So what y values does that function take on? It seems like it's going to take on all the values that are 0 or greater. And we see that's certainly nothing negative. So so maybe we could write y is greater than or equal to 0. But that's important because that tells us our domain here. So our domain here is x is greater than or equal to 0. Because we know that the range from one becomes the domain of the other. And this is going to be a very important fact for us whenever we start graphing these things. One additional thing, if you're confused, why did that y turn into an x, just write it in interval notation, 0 to infinity, because then you don't have to worry about a particular variable. So there. If you're concerned about this y turning into an x, just write your range and domain and interval notation. Okay, so that should be enough examples to get you going, at least for the initial part of this homework.